Hello, I'm Russ Baker. In this segment, we're going to discuss the geometric sequence and series. We're going to calculate any term of a geometric sequence, find the sum of n terms, find out when and how to find the sum of an infinite series as well. What is a geometric sequence? A geometric sequence is a sequence defined as any sequence value a sub n equals the first term a sub 1 times r to the n minus 1 power. R is called a common ratio, and n is the number of the term to be found. Let's start with an example. Let's find the fifth term, a5, and the general term, a sub n, for a sequence whose first terms are 4/5, 2, 5, and 25 halves. 4/5, 2, 5, 25 halves, we want the next term. A sub n equals a sub 1 r to the n minus 1 power. In our case, we have n as 5, so we want to take the first term, which is 4/5, and find r. Well, what's r? Well, the common ratio is the ratio of any two terms. The easiest ones to look at here are 5 and 2. So r is equal to 5 divided by 2. That's our common ratio. That ratio will be the same no matter what two different elements we choose to put in our ratio, where we take one element and divide it by the previous one. So now we can go back and we can put in r as 5 halves, and n is 5, 5 minus 1 is 4. We can now go ahead and do our arithmetic. 4/5 times 5 to the 4th power is 625, and 2 to the 4th power is 16. Multiplying that all out, we'll get 125 fourths for A5. We were also asked to write the general term, which can be done by writing the first term and the r, which we know is 5 halves, and the n minus 1 power. We could now use this particular equation to find any other sequence entry. Now let's analyze a sequence in which we know two non-sequential sequence values. Find a1 and r for the geometric sequence if a sub 3 is 5 and a sub 8 is 1 over 625. We take what we know, that again a sub 3 is 5, a8 is 1 over 625, and we'll put that in our formulas for the general term. We know then that a3 is equal to a1 times r to the 3 minus 1 power, so that's r squared. Likewise, we know that a8 is equal to a1 times r to the 8 minus 1, or 7 power. Let's solve each one of these for a1. a1 on this side is a3 divided by r squared. On this side, a1 is equal to a8 divided by r to the 7th. We can now equate the two fractions since they're both equal to a1. a sub 3 over r squared equals a sub 8 over r 7. Let's substitute in now the values that we know for a3 and a8. We'll have 5 over r squared equals 1 over 625 over r to the 7th. And this will be much easier to look at if we cross multiply. This is what we'll have. We'll have 5r to the 7th, as you can see cross multiplying here, and r squared over 625. Okay. Now we'll divide both sides by r squared. That will give us 5r to the 5th equals 1 over 625. And divide both sides by 5, and r to the 5th equals 1 over 3,125. To finish, we need to take the 5th root of both sides, and that will give us r equals 1/5. If r is 1/5, we can go back now and say, well, we knew that 5 was a1 times our r now, 1/5, and that was our a3, and so this is squared. If 5 equals a1 times 1/5 squared, that's 1/25, and so we multiply both sides by 25, and we find out that a1 is in fact 125, and we've done what we set out to do. We found our a1, and we know r is 1/5. Sometimes we want to add together the sum of the first n terms of a geometric sequence. That can be accomplished using this formula. If a geometric sequence has a first term a1 and a common ratio r, then the sum of the first n terms, s sub n, is a1 times the quantity 1 minus r to the nth power over 1 minus r, where r is not equal to 1. Let's practice that using that formula in this particular example. We'll use the formula for s sub n to find the sum of the first 5 terms for the geometric sequence 2, 8, 32, 128, and so on. We take what we know first, that we have a sequence 2, 8, 32, and 128. In order to use the formula, we know that a1 is 2. Now we need to find out what r is. We can take any two of these given entries. How about if we take 32 and divide it by 8 and find out that r, in this case, turns out to be 4. Now we'll go back and substitute in to our formula. S sub 5 equals a1 times 1 minus r, which is 4, to the n power, which is 5, all over 1 minus r, which again is 4. Now that arithmetic will give us what we need for our final sum. Let's see. 2 times 1 minus 4 to the 5th power is 1,024. And, of course, 1 minus 4 is negative 3. Continuing to simplify, we have 2 times 1 minus 1,024 is negative 1,023 over negative 3. And when we do that calculation, we will find that we have the sum of 682. Now I'd like you to try using this formula on your own. Use the formula for S sub n to find the sum of the first 5 terms for this geometric sequence: 18, negative 9, 9 halves, negative 9 fourths, and so on. Turn off the tape, do your work, and then come back. I hope you got your answer all right. We'll take a look at it and solve it just the way we did the previous problem. We know our given terms are here. we know that our first term is 18. We know that R is found by taking any two terms. I guess I'd like to take the whole number terms. They're easier to think about, aren't they? And write negative 9 over 18. So our R is negative 1/2. Negative 1/2. We want to find the sum of the first 5 terms. So we'll substitute the fifth sum, n is 5. We'll put in our first term is 18. 1 minus negative 1/2 raised to the 5th power, all over 1 minus negative 1/2. We have only to do the arithmetic now. We have 18 times 1 plus 1 over 32, all over 3/2. As we continue to simplify, that's 18 times 33 over 32 over 3/2, which would give us 36 times 33 over 32 over 3, which would give us 12 times 33 over 32, which eventually will reduce down to the sum I hope you got for your answer, 99 over 8. Let's try one now with summation notation. Let's find the sum of 2 to the k power for k equals 4 to 10. We can find a 1 by substituting k equals 4. That's 2 to the 4th power, which is 16. Now we also need r, but in order to find r, the common ratio, we need to find another a. So let's find a2. A sub 2, the second term, is 2 to the 5th, and that's 32. Now we can find r by taking a2 divided by a1 and see that our common ratio, which you might have guessed, is 2. So we need to find the sum of from 4 to 10. Now you might take a minute to try to figure out how many terms there actually are. We could say that there's 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. That's 7 terms. Another way to get that is to say I'm going to subtract 10 minus 4. That gives me 6, plus 1 for the end point, if you will. So what we're looking for is S, the 7th sum. The 7th sum is the first term times 1 minus r, which is 2, raised to the nth power, which is 7, and divided by 1 minus 2, which is negative 1. Now we have 16 times 1 minus 128 over negative 1, which is negative 16 times negative 127, and negative 16 times negative 127 is 2032. Let's verify our result with the graphing calculator. We want second function and list. We'll go over to the math option and push 5 for sum. Then second list again, this time stopping at operations, but 5 again for sequence. Now we put in our formula for the sequence, which is 2 raised to the x power. Enter that our variable is, in fact, x. and that we are interested in the sum from the 4th term up to the 10th term. Close parentheses for the sequence, close parentheses for the sum, and enter. And we see that our answer is confirmed at 2032. In an infinite geometric sequence, if the common ratio is between -1 and 1, the sum will actually converge to a specific value. We can find that value using this formula. The sum for an infinite geometric sequence with a first term a1 and a common ratio r, if r is between -1 and 1, is given by the infinite sum is equal to a1 over 1 minus r. This does not apply if r is not between -1 and 1. Let's consider a sample. If the series converges, find the sum of the series 4/3 plus 2/3 plus 1/3 plus, and so on. We'll use the formula. The infinite sum is equal to the a1 divided by 1 minus r. First, we need to find out whether or not this actually is a convergent series. We'll do that by finding r. a1, the first term, is 4/3. The second term is 2/3. And so r can be found by taking 2/3 and dividing by 4/3. The 3's will cancel out, 2/4, and r is 1/2. r is 1/2. We now know that since r is between -1 and 1, that the infinite series does converge. Let's see what the sum would be. It's the first term, 4/3, divided by 1 minus 1/2. Let's simplify. 4/3 over 1/2, which is 8/3. That's the sum of the infinite series. No matter how many terms we choose to add, the value will get closer and closer to 8/3. Let's end our lesson with an application problem which involves the geometric sequence. Let's find the future value of an annuity with payments of $2,430 at the end of each year for 10 years at 6% interest compounded annually. Let's take our information. We know we're paying $2,430 annually. We're getting 6%. We're going to do this for 10 years, and our payments are made at the end of the year. We can treat each payment as if it was a separate account. That means that each payment gets one less year's interest than the payment before. That also means then that the last payment will get no interest, and the first payment will get 9 years interest because it's paid at the end of the year. We have a formula that says 2430, our payment, that the interest it earns is 1.06 to the nth power. We can therefore say that this is our sequence. And the sum of 10 years of this sequence looks like this. We pay $2,430 at 6% interest. The last payment we make gets no interest. Plus 2430 times 1.06 to the first power, and so on until we get to 2,430 times 1.06 raised to the 9th power. That's actually the first payment we made. We can rewrite this until it looks like this. The 10th sum would be $2,430, the individual payment, times the sum from k equals 0, the last payment, all the way up to 9 of 1.06 raised to the k power. In order to solve this problem, we'll go to our graphing calculator and enter this information into the sequence values. We'll clear our previous work, but do second list math sum, second list operations sequence. Now the equation for our sequence is 1.06 raised to the x power, where x is our variable, and we want a 0 to 9 terms. Close the sequence, close the sum, and enter. That value needs to be multiplied by the $2,430 value each year, and we find out that at the end of the term we have $32,029.33. There are many, many applications for geometric sequence and series. You should memorize the formulas that go with this section and practice both by hand and with your calculator. Search for other finance capabilities of your calculator as well.